we've investigated the long-run precipitation generating processes and how they vary seasonally across the national territory of Costa Rica. As human beings, we're very adept at living in various conditions, ranging from polar regions in the Arctic to the Sahara Desert to the rainforests of Central Africa and the Amazon. So we're very good at adapting to different conditions. It is, however, the variability from year to year which makes life very difficult for us. Whether we're going to be planning water resources, whether we're generating hydroelectricity, whether it's farming or fishing, a whole set of variety of human activities rely on us being able to get a reasonable estimate of how much precipitation, how much water there's going to be in the system in the future. In this little lecture, I want to take a look at the major causes of climate variability here in Costa Rica. The single phenomenon known as ENSO, or more popularly known in the press as El Nino and its compatriot La Nina, are in fact a twinned pair of phenomenon. ENSO stands for El Nino, which is the oceanic component of a oscillation which occurs along the equatorial Pacific. The SO part stands for Southern Oscillation, which is an associated change in atmospheric pressures, which often goes hand in hand with El Nino. So this is sometimes called ENSO. And Costa Rica is no exception to the rest of the world in that in many cases ENSO itself is one of the causes, the single largest cause of interannual variability. This is the very familiar pattern of conditions during the Northern Hemisphere winter in about February. We can see that the northeast trades are the dominant driving force for much of the climatology of Costa Rica. We can also see that the major rainmaking machine for the Pacific coast, the intertropical convergence zone, is located at about 3 degrees north. We said that this should, theoretically, be much farther south following the position of the overhead sun. The reason it's not in this particular location in the world is the cold Peruvian Humboldt Current, shown here as that dark blue arrow. The waters are so cold that it prevents that migration of the intertropical convergence zone. Now, during El Nino conditions, these usually cold waters off the coast of Ecuador and northern Peru are replaced by warm waters flowing backwards from the western side of the Pacific towards the east coast here. So the first thing that happens often during an El Nino is that the warm waters appear in the eastern equatorial Pacific in November and December off of the coast of Ecuador and Peru. Hence its name El Nino, the boy child, arriving, generally the fishermen recognized, at the time of Christmas. These figures here are from NOAA, the National Oceanic and Atmospheric Administration, and the upper diagram shows us a variability of sea surface temperatures in degrees Celsius. So 0 on this graph, on the vertical axis, represents the long-run average sea surface temperatures at a location in the Pacific known as Nino 1 plus 2. In the lower diagram, you can see Nino 1 plus 2 circled in black. It's the small red square there that we've just been talking about. Along the horizontal axis of the upper diagram, we have time from 1950 here up to about 2015, a year ago. You can see there's a series of oscillations as the sea surface temperatures go above average, below average, above average, below average, in a fairly rhythmic sort of pseudo-periodic fashion. So if you cast your eye along to perhaps 1982-83, which was an extremely large El Nino event, or again the 1997-1998 event, you'll see that there's a very large red spike. The sea surface temperatures here rose as much as 4 degrees Celsius, perhaps 8 degrees Fahrenheit warmer than normal. So our little diagram showing the sea surface temperatures getting warmer is not an exaggeration. The zones showed in blue are when the sea surface temperatures are colder than normal, negative anomalies, perhaps as much as 2 degrees Celsius cooler than normal. And these have become known as La Nina, the opposite phase, if you like, of El Nino. The importance of these waters, sea surface temperatures of these waters to Costa Rica is that it controls the position of the intertropical convergence zone, that rainmaking machine for the Pacific coast. As the warm waters enter into the area of Ecuador and Peru, this allows the intertropical convergence zone to move further south and west than its normal position. So our rainmaking machine has now moved much farther south, and even this year in 2016, 2017, it moved so far south that it caused tremendous floods along the coast of Peru, which is normally a desert. One other observation that has been made by climatologists is that during an El Nino year, the strength of those northeast trades intensifies. They become much stronger. And so you can see on my diagram here, I've made the arrow much larger to emphasize that. So here's the linkage with the ITCZ, the major rainmaking machine in the Pacific coast, and the northeast trades and its corollary, the Caribbean low-level jet, which we know are one of the major controls on precipitation on the Caribbean coast. We also know that the northeast trades and the low-level jet control the veraneos, this small period of midsummer drought. Just to refresh your memories, these square diagrams are cross sections through the Caribbean Sea at about 80 degrees west of the prime meridian. What they're doing is they're indicating for us something about the behavior of the trade winds and the Caribbean low-level jets. These are seasonal observations, so you can see over on the right-hand side MAM for March, April, May, which we would call the sort of northern hemisphere spring. Different from the diagrams we saw before, what these figures are showing are the difference in velocities between what are called the warm phases of ENSO and the cold phases of ENSO, which you can basically think of as the difference between El Nino and La Nina conditions. So here we're trying to get at some measure of the variation in this big rain-making component, the trade winds and the Caribbean low-level jet. When you see colors in the red part of the spectrum, reds, oranges, then this is telling us that the winds have become more westerly. That is, that they are less easterly than we thought. So this would mean that the trade winds have become weaker. If you see blues, purples, then these are negative values, which is telling us that during warm phases, the westerly component is less, and the easterly component is increased. So this is telling us in this, if it were to be blue, that our easterly winds have intensified. Once again, the latitudinal range at the 80 degrees west longitude is shown along the horizontal axis of the little square diagrams, going from 8 degrees to 20 degrees, and the white vertical lines roughly indicate the latitudinal range of Costa Rica. So in this figure, you can see that for March, April, May, I've got basically an orange blob in the middle, and the orange blob is telling me that the winds are then more westerly, which is actually telling me that the trade winds in March, April, May have slightly weakened by about 1 meter per second. Other than that, there's very little change in the conditions in the trade winds between warm phases of ENSO and cold phases of ENSO. As we progress to June, July, August, our northern hemisphere summer, then we can see that the figure is now dominated by colors in the blue component. Blue, you'll see, means that we have more easterly winds. The winds are more easterly than normal. These are our northeast trades, so this means that the trade winds and the Caribbean low-level jet have intensified. How much have they intensified? Well, we can see we've got 1, 2, 3, 4 meters per second in this very core of the Caribbean low-level jet there coming in towards Nicaragua and Costa Rica. You can see that it's flowing 4 meters per second faster in El Nino years than it is in La Nina years. And remember, if you cast your mind back to the earlier lecture, then on average the speeds here were somewhere about 10 to 12 meters per second. So we've got perhaps a 40% increase in the velocity of the winds during El Nino events, much stronger. So in El Nino the trades become stronger, they're westerly, they're stronger than they are in La Nina years. Here's the figure for September, October, November. Once again, the pattern is dominated by blues. This time the blues are not as intense, perhaps minus 1 meter per second faster in El Nino years, 2 meters per second faster in La Nina years. Now you remember that normally in September, October, November, the trade winds subside, the low-level jet becomes a little weaker. So we've got to realize that this change is superimposed upon a general weakening of the Caribbean low-level jet in September, October, November. So in the Northern Hemisphere fall, it's usual in El Nino years for the trades to be stronger, but not as strong as they were in June, July and August, than they are in La Nina years. Right. In our earlier discussion of the rainfall generating mechanism of fronts coming down from North America, the nortes in Costa Rica, we didn't talk too much about them. They weren't that important. But if you look at this diagram, you can now see the dominance of colors in the red side of the spectrum. This is telling me that in warm phases during El Nino years, the winds have become more westerly, or that means that the trade winds have become much less speedy than they were before. They've become less easterly. So in an El Nino year, in the December, January, February, following an El Nino year, we see that the trade winds actually weaken now. What does this mean for Costa Rica? Well, the hydrologists often study river basins rather than studying rainfall stations. And the reason that we do this is that river basins integrate a variety of effects from a big spatial area. So basically here we've got two stations. One, the Rio Sarapiqui, which drains towards the Caribbean on the Caribbean flank of the Cordillera Central. And we've got the Rio Candelaria, which flows towards the Pacific from the northern flanks of the Cordillera Talamanca. And we're going to take a look at the flood characteristics of these two rivers as they vary between El Nino years and La Nina years. Here is the evidence to support the proposal that the stream flow represents the rainfall which is going into these basins. On the top of this diagram we've got data for the Rio Candelaria, and the bottom diagram is for the Rio Sarapiqui. Along the top axis we've got months starting in May, June, July, August, September, October, November, and ending in April. Along the lower horizontal axis we've got days since April of the 30th, so basically every 30 days represents a month. What you're seeing here is a trace of the long run average stream flow in blue on that particular day. The thinner red lines, one side or the other of the blue line, represent the mean plus 1 standard deviation and minus 1 standard deviation to give us some idea of variability from year to year, which we said is very much what we're after in this particular part of the study. You can see in the Rio Candelaria just two peaks. There's an early peak here in June, May and June, and then the river drops off just a little in the Veraneos and comes back very strongly in September, October, and then starts to decline November and through to December when we're into the dry period. Why isn't that first peak of stream flow as large as the second peak, even though we know that the rainfall is quite considerable in May and June? Well, you have to consider that the rain in May and June is falling on soil which has basically been drying out since about December. So for about 6 months during the dry season, the soil has been drying out. When the first rains recur in May, then that tends to be absorbed by the soil and not go directly to the river. By the time we reach the second peak of rainfall after the veranieos, the soils have become saturated and the water runs off more quickly and more efficiently and more effectively into the river. So there we have our two peaks, one in May and June, the other one in September, October, separated by the veranieos. The lower diagram represents the similar data, but in this case it's for the Sarapiquí. We also see a double peak there, which we saw in the rainfall records. We have a peak somewhere in July and August, and then it drops off into September, October, and once again it peaks in November, December, and drops off a little in January, February, March, etc. The July-August peak corresponds to the maximum intensity of the trade winds and the Caribbean low-level jet. The peak in November-December also corresponds to an intensification of the Caribbean low-level jet, at the same time as we know that we occasionally get cold fronts bursting out from North America. So now you can see that there's tremendous variability from year to year in the rainfall that we're likely to experience in December. It can be very high, it could be very low. So a lot of variability on this side, but as with the rainfall, the streams are always flowing. There's very high discharge in most days of the year. This figure summarizes the number and timing of floods on the Rio Candelaria on the Pacific slope of Costa Rica. On the x-axis we have time, with the months marked out across the top axis from May through to April, and the equivalent days since April the 30th along the bottom axis. On the vertical axis we've got some measure of the intensity of flooding. This is indicated as the average number of floods observed up to and including the date along the x-axis. So for instance, if I look along the bottom x-axis to day 120, which is the end of August, and I read up to the blue dots, you'll see that on average I have about one flood per year before the end of August. If you read along 60 days later, 2 months later, to the end of October and read up to the blue dots, you'll see that on average I have had 3.5 floods up to that date in the year. The steeper the line, then the more frequently floods occur in that period. When the line becomes horizontal, no floods have been observed in that period. The record for the Rio Candelaria is divided into two categories. One category are years which are classified as La Nina years, cold phase ENSO, the blue circles, and the other one is El Nino years, warm phases of ENSO, the red squares. You can see here that overall the blue dots always plot up higher than the red squares. This is telling us that floods are far more frequent in La Nina years than they are in El Nino years. You can see that perhaps there are 3 times as many floods by the end of October in a La Nina year than there is in an El Nino year. You can see that there is a very distinct clustering of the blue dots between September and October. That is also matched in terms of the timing, in terms of the red squares. So we know this is the post-veranieos period of intense rainfall in September and October. So the timing has remained the same, but the intensity of the flooding, the amount of rain being delivered, has clearly differed. If we look at day 30 to day 60, there in May, June, the pre-veranieos period, there's an interesting anomaly, which is just these 2 red dots, which suggests that, strangely, in an El Nino year, it almost seems that there's a greater likelihood of flooding early in the year. And we actually saw this when we looked at the strength of the Caribbean low-level jet in March and April. We saw that it was actually weaker than normal in an El Nino year, which would have meant that the rain shadow effect would have been less, and therefore this is probably reflecting that very small change. Another thing I'd like you to take a look at is the long stretch where the line is horizontal on the red squares between about the beginning of June and middle of September. In El Nino years, no floods have been observed in that time period. Now this is the time period that corresponds to the veranieos. And so you can see that what's happening is that during an El Nino year, the veranieos become very pronounced and very long. Compare that to the slope of the blue lines, the blue line joining the blue dots, during the same time period. You can see that it never completely levels off. It continues to rise. So even though the veranieos is there, it doesn't last as long. You can see that the first floods are starting once again on about day 120, and it never really stops raining. You can see there's that blue dot at about day 90 there. So on the Pacific side, we're seeing, as we might have expected, more floods in La Nina years, fewer floods in El Nino years. We're seeing a longer veranieos in El Nino years and a virtually non-existent veranieos in La Nina years. There's also this little interesting observation which subsequent research is picking up as well, that actually we've got perhaps a greater likelihood of more rain and more floods in El Nino years in the pre-veranieos period during a El Nino. You can see there have been no floods whatsoever after November, because December, January, February, we're completely into the dry period in Costa Rica, whether it's an El Nino year or a La Nina year. Here's a similar diagram for the basin on the Caribbean side, the Rio Sarapiquí. Once again, you can see the two periods of rainfall shown clearly with the red squares. There's a very steep rise, increase in flood chances at about day 90, which represents July to August. So this is the time, at least here, of the red squares, where we know the Caribbean low-level jet intensifies and delivers more precipitation to this coast. And then we get a period, September, October, which remember is the time of maximum flooding on the Pacific side, where there's virtually no flooding at all on the Caribbean side. This is when the Caribbean low-level jet declines. And then it picks up again, the storms, the floods pick up again, November, December, January, February, which is a combination, we think, of the Caribbean low-level jet and the cold outbursts of rain coming down from the North American continent. What's very different about this diagram from the previous one is that the red squares plot up higher than the blue circles. This is telling us that overall, on the Caribbean coast, we're more likely to get floods, perhaps twice as many floods, 1.5 times as many floods, in an El Nino year as we are a La Nina year. The opposite to what we saw on the Caribbean, on the Pacific coast. When it's a La Nina year, the trade winds have become so weak in the veranieos, July, August time, that they've produced no floods. There are no blue dots in that time at all. So this actually matches again what we saw on the Pacific coast, which was that during a La Nina year, the veranieos basically doesn't exist. It ceases to exist. But what is interesting about the conditions during the cold phase, the blue dots, is that they rise very steeply in this time period, November, December, January, February. They're actually more likely to be flooding in November, December through to January on the Caribbean coast than there is, in a La Nina year, than there is an El Nino year. And this seems to have something to do with the frequency of the outbursts of cold air from North America. You'll remember that we saw that the trade winds in this time period became weaker in an El Nino year. And that appears to allow for greater incursions of cold air from North America producing these floods here, which are related to those nortes which come down, sweep down and hit the Caribbean coast. Because Costa Rica sits between the Atlantic Ocean basin and the Pacific Ocean basin, and we know that the two major rain-making machines are the northeast trades driven from the North Atlantic and the intertropical convergence zone driven from the Pacific, a second factor should be considered in the climate variability. And that second factor is what's happening to the sea surface temperatures in the subtropical North Atlantic. This diagram rather mirrors the one we saw earlier in red and blue. On the vertical axis, we've got a measure of sea surface temperatures anomalies, again in degrees Celsius. So once again, 0 represents long run average. Positive numbers means that that particular ocean is warmer than average. Negative is cooler than average. The open bars represent sea surface temperatures on the equatorial Pacific at about the international dateline. This region of the globe is called Nino 3-4. The coloured or the filled in columns, the black columns, represent sea surface fluctuations at the subtropical Atlantic off of our coasts of Florida, somewhere between about 20 and 30 degrees north. And you can see that over time, those two fluctuate, are above average and below average. It's probably the interaction of these two which together are going to produce differences in climate responses and variability from year to year. Life becomes more complicated because these two systems seem to be out of phase with one another. Firstly, the sea surface temperature ranges associated with Nino 3-4, the open bars, have a higher amplitude. They're larger anomalies. And secondly, the frequency with which the two of these seem to oscillate are different. The North Atlantic seems to change more slowly over long periods of time, whereas the El Nino has a typical sort of pseudo frequency of somewhere between about 5 and 7 years. However, this changes markedly when we look at the July-August season, the season of the veraneos, when we know that the Caribbean low-level jet is intensifying. And you can see that during the warm phase years, where we know the trade winds really strengthen, that now along that Caribbean coast we've got monthly rains or seasonal rainfalls which are 1.5 standard deviations above the long run mean. There's a tremendous gradient running right down the Cordilleras there, and on the Pacific side we've now got standard deviations in the order of half a standard deviation, 1 standard deviation below the long run mean. So we can see that the veraneos period is a period which is particularly susceptible to changes in phase, particularly the El Nino conditions, where it'll be raining very hard simultaneously on the Caribbean coast, while the Pacific coast is experiencing extensive droughts. For a small country, this is a tremendous burden. We've got two disasters occurring simultaneously. Flooding, roads being washed away, wells being polluted on the Caribbean side. On the Pacific side, rainfalls 10, 15, 20% lower than normal, crops in danger, reservoirs emptying, hydroelectric power in doubt. So what we can see here is the response the response of rainfalls to a El Nino and a La Nina are reversed. We can see the reds and the blues have switched either side of the Cordillera. We can see that the impact of the warm Pacific, i.e. an El Nino condition, is much more marked than that of a La Nina condition, cold condition. Why is this? Well, we know that our trade winds are intensifying during an El Nino condition at this time of year. That means our Caribbean low-level jet is blowing much stronger, which means that the veraneos on the Pacific side are greatly extended as the warm water is blown off of the Gulf of Papagayo out into the Pacific Ocean. The season, September and October, represents the height of the rainy season along the Pacific slope. We can see from this diagram that during an El Nino, warm phase, and so warm Pacific, that the conditions of excess rain on the Caribbean, deficit rain in the coastal regions of the Pacific persist. Perhaps not as marked. Now we can see we're perhaps half a standard deviation above and below the long run mean, but this is the wettest time of the year, and these are quite marked decreases and increases in precipitation. We can also see that perhaps the response to the La Nina phase here is more marked than it was in July and August. There's some very dark red, dark blues along this coast. So the impacts are less pronounced than in the Veraneos. There's still a marked contrast between the two coasts. They both flip under the conditions of warm phase or cold phase Pacific. We can see that the displacement of the ITCZ south and west of its normal position is having a tremendous effect upon rainfall along the Pacific coastal region, and also that the cooler waters off the coast, off the peninsula, the Nicoya Peninsula, and the coast Gulf of Papagayo are still having a very large impact. So how might conditions in the Atlantic amplify or mollify the effects of El Nino? We know that the northeast trades are coming from the subtropical North Atlantic. We also get a sense that what's happening in the Atlantic may affect the fronts. So we're expecting to see some form of reinforcement or negative negating one another in terms of these impacts. For this, we're going to have to go back to our very poor general circulation model here. So here's our globe. We have our high atmospheric pressures roughly 30 degrees north, our low atmospheric pressures somewhere in and around the equator, our intertropical convergence zone. The reason there's high atmospheric pressure at 30 degrees north is that the ocean waters at these latitudes remain cooler than the land. Now, if the North Atlantic sea surface temperatures for some reason were to become even cooler than normal, then the atmospheric pressure above those oceans would become even higher. Likewise, if we were to see the sea surface temperatures underneath the subtropical North Atlantic becoming warmer, then the atmospheric pressure above that ocean would become less high, would become lower. Now, the difference between the high pressures and the low pressures is what's driving the winds from one place in the world to another. So, the higher the high and the lower the low, the faster the winds are going to move between the two. So, if we have high atmospheric pressure at 30 degrees north and we have colder waters, then we'd expect to see those trade winds becoming stronger with all the results that we've already anticipated. If from one of those times of the century, those decades, when sea surface temperatures in the Atlantic are warmer than normal, then we can expect that the trades will become a little bit weaker. So these are the diagrams again, but now we've done a fourfold differentiation. These are for the July-August time, which we know the Veraneos is one of the more sensitive times of the year in Costa Rica to these causes of climate variability. The top pair give us cold Pacific, warm Pacific, but now they're under conditions when we have a cold Atlantic. So the top left-hand diagram of those set of four represents deviations in July-August rainfalls when there's both a cold Atlantic and a cold Pacific. The figure in the top right represents the deviations in rainfall that we anticipate when there's both a cold Atlantic and a warm Pacific. Now, a cold Atlantic and a warm Pacific are going to make those trade winds very strong indeed. And we can see then that the response to an El Nino or warm Pacific under those conditions is very marked, as indicated by the sharp contrast between the deep blues on the Caribbean, lots of rain, heavier than normal, and the deep reds over here in the Gulf of Nicoya and Guanacaste, showing us very much lower rainfalls than normal. The bottom right hand diagram here shows conditions of a warm Pacific, but now these are, well, we've got a warm Pacific and a warm Atlantic. And now you can see in that bottom right hand figure, even though sea surface temperatures in the Pacific are above average, the fact that the northeast trades are not being driven by a cold Atlantic and are weakened because it's a warm Atlantic, that pattern breaks down markedly and almost seems to reverse. Similarly, we can see that the impacts of a cold Pacific, a La Nina condition, are a little bit weak in times when we have a cold Atlantic. But if we combine a cold Pacific with a warm Atlantic, then we're going to get excessive rains in Nicoya, the Central Valley, and the Pacific coastal region. And we're going to get excessive droughts along the Caribbean coast. Here's the peak of our rainy season, September, October, at least the peak of the rainy season along the Pacific coast. Once again, what happens to these rainfall records if we have a cold Atlantic in combination with a cold Pacific in the top left? Well, we can see that under those conditions, most of Costa Rica is going to get extra rainfall in September and October. Only the northeasterly part of Costa Rica is going to get a drought. If we have a cold Atlantic and a warm Pacific, then once again with these strong trade winds, we find the rain shadow effect is very marked, and that the coastal conditions along the Pacific are of a drought and excess rain along the Caribbean. Once we weaken that signal by having a warm Atlantic, the bottom pair of diagrams, you can still see there's a flipping of conditions between cold Pacific and warm Pacific, but that impact is not as marked. So you can't only use the fact that it's going to be an El Nino year or a La Nina year to give you some idea of the extreme that's likely to follow, but you also need to know something about the behavior in the Atlantic. Generally speaking, if it's a cold Atlantic in combination with a Nino, you're going to get the most extreme conditions on either side of the country. Floods on the Caribbean, drought in the Pacific. One last diagram here, which is very interesting, at least I think. This is for November and December. And you can see that we have our normal standardized deviates again. But I want you to look at the big blue area around the San Juan lowlands here during a warm Atlantic and a cold Pacific. So this would be a La Nina condition when the Atlantic is warmer than normal. And you can see that this area most prone to nortes, to the cold fronts, seems to be getting excess rainfall. So these guys, where we know that we have this unusual winter maximum, we saw it in the Sarapiquí in terms of the flooding, these are going to be years of exceptionally excessive flooding. If it was a La Nina, cold Pacific, and a cold Atlantic, then you can see in fact that the fronts are not coming down at all. That same area in that top left hand graph is now red, not blue. It's a drought. And in fact, you can see that whenever there's a cold Atlantic, in November, December, the Caribbean coast tends to be in drought conditions. And whenever there's a warm Atlantic, the Caribbean coast seems to be in excess rain conditions. And so the big contrast here is not El Nino, La Nina conditions, but warm Atlantic, cold Atlantic.